Go.
Section 6.2, determinants. Definition. We're going to start with definition of determinant of 2 by 2 matrix. So determinant of 2 by 2 matrix D. Matrix consists out of 4 numbers A, B, C, D is calculated by the next rule. A, D, we multiply diagonal elements and then subtract contra-diagonal elements C, B. Determinant is one number which we connect to the matrix. Does not matter like how big is the matrix. The only condition is the matrix must be square matrix. For example, it's 2 by 2 matrix or 3 by 3, 4 by 4. These bars also mean determinant. Means that if you don't write down D, but just write down bars, still gonna be determinant. If you wanna just do the matrix, it's a square brackets. Okay, let's calculate determinant of something. Example. Let's calculate determinant of the matrix 1, 2, 3, 4. Well, remember, by the formula, we multiply 1 by 4 and subtract 2 by 3. 2 by 3. 1 by 4 is 4, 2 by 3 is 6, and determinant is equal to negative 2. Is it? Let me double check it. 1 by 4, 2 by 3. Okay. Now, properties of determinants. Let's start with proving some properties which are going to be like general properties of determinants, but we're going to check all of them on determinants 2 by 2. Property number 1. If we have a determinant of matrix A, B, C, D, and we switch rows, put first row second and second row first, the determinant of matrix C, D, A, B is going to be equal, according to the formula, product of diagonal elements minus product of A by D. If you compare it to original determinant we have for original matrix over here, you're going to see that that's basically the very same determinant, just with minus in front of this term and plus in front of this term. That's minus AD BC, which is just the determinant of A, B, C, D matrix. So what happens? If you switch rows in the matrix, determinant is going to change the sign. The rule works not only for 2 by 2 matrix. We checked it for 2 by 2, but it's going to work for 3 by 3, 4 by 4, and so on. Eventually, in linear algebra, you are going to prove it. For right now, it's easier to remember if you just try it on 2 by 2 matrix. Rule number 2, or property number 2. If you have a matrix AB 0, 0, matrix with one row equal to zeros, the determinant is going to be, let's just calculate it, A by 0 minus B by 0 is going to be just 0. So the rule is going to work for all matrices for which you can calculate the determinant. If you have a row of zeros, the determinant is 0. Okay, I'm going to erase these 2 rules and put more rules. Actually, we have up to 6 rules, so I'm going to erase them a lot. Well, next rule, rule number 3. If you do have a matrix with identical rows, something like this, let's calculate the determinant of it. That's A, B minus A, B. So we are going to get 0. So if you do have 2 identical rows in the matrix, the determinant is 0. That again works for all matrices, not only for 2 by 2. Rule number 4. If you multiply one row of the matrix by a constant A, K, what is going to be the determinant? How the determinant is going to change? Well, I'm just going to calculate it. That's K, A multiplied by D minus K, B multiplied by C. Because K repeated here and here, I'm going to take it out and have AD minus BC, which is actually a determinant of original matrix A, B, C, D. So when you multiply one row by any arbitrary number K, non-zero of course, the determinant is going to be 0, is going to work too, but no one is doing this. You are going to have determinant multiplied by this number K. The resulting determinant is going to affect the determinant. Okay, rule number 5. Imagine that you take one row of the matrix and add it to another row of the matrix multiplied by k. For example, I'm going to write it down and then explain how it works. Plus kd cd. So what I did over here, I took row number 2, which was cd, multiplied it by k here and here, and added it to first row. So I did row operation. How it's going to affect the determinant? Well, let's check. I'm just going to calculate literally the determinant and show you how it's going to affect. So I'm going to have A plus KC multiplied by D minus B plus KD multiplied by C. Let me simplify this expression. AD plus KCD minus BC minus KDC. So what I have a term which has factors K, C, D. And this term has same factors, just in different order, K, D, C. Well, because they are coming with different opposite signs, they cancel each other. What is going to happen, what is going to be left over? AD minus BC, which is actually just determinant of original matrix. So actually, when you do row operation on the matrix, determinant does not change. You can multiply any row by any number, add it to another row, and get the very same determinant. And okay, the last rule, I don't have space here, I'm going to erase first. This four rows. Rule number 6. If you do have a matrix A, B, 0, D, this is a triangular matrix, right? Do you see it? Or let's say, try to draw it like this. Calculate the determinant. You are going to find out that determinant is AD minus B multiplied by 0, which is going to be just AD. Well, interestingly, that determinant of any matrix, if you bring it to diagonal form, is going to be just the product of diagonal elements. And if you bring it to upper triangular form, same. So you just multiply diagonal elements, and that's going to give you the determinant. Well, here is a elementary case when non-diagonal element just 1 and it equals to 0, but it's going to work for bigger sizes. Well, we remember that determinants are defined only for square matrices. So 2 by 2, 3 by 3, 4 by 4. So 2 by 3 is not going to have a determinant. Okay? And for example, I'm going to give you an example of rule number 6. For example, we have matrix 1, 2, 3, 0, 4, 5, 0, 0, 6. If you want to calculate the determinant of this matrix, it's still going to be the product of diagonal elements. So we're going to have 24. Okay? Well, guys, we do have 2 ways to find determinants of 3 by 3 matrix. We know how to find 2 by 2 by the rule, right? For 3 by 3, there are 2 ways. And unfortunately, I cannot prove either of these 2 ways in this class because it's actually subject of linear algebra. So I'm going to explain you how the rules are working. You choose which one you are going to use. Normally, I'm not going to use matrices higher than the 3 by 3. So let's deal with determinants of 3 by 3 matrix. Determinant of 3 by 3 matrix. Well, way number 1. Use row operations and bring it to upper triangular matrix. Multiply diagonal elements. Way number 2, and you can find way number 2 explained in the book. Decompose the matrix or expand the matrix across the first row. I'm going to show you how the rule is going to work, but to explain it, it's going to require maybe 2-3 hours of lecture, so I'm not going to explain why it's working like this. So Fortunately or unfortunately, for 3 by 3 matrix it's going to be much faster than do row operations. But for higher order matrices, maybe these two methods can compete. So I'm going to consider 3 by 3 matrix, and my first row consists out of A elements, A1, A2, A3. My second row B elements, and my third row C elements, C3. So to expand the determinant by first row, we're going to take first element, A1, and multiply it by determinant of the matrix which is left over if you cross the row and the column which have this element. So determinant is going to be B2, B3, C2, C3, minus just the row. And cross element A2, leftover matrix is going to be B1, B3, C1, C3. And then plus again, and we are going to have leftover matrix B1, B2, C1, C2. B1, B2, C1, C2. Okay, let's consider example of use this weird way number 2, expansion by the first row. So my example is going to be just calculation of determinant of the matrix. 1, 2, 3, 2, 1, 2, 0, 3, 1. I just use arbitrary matrix. So first element 1 and the determinant of 1, 2, 3, 1. 1, 2, 3, 1, leftover determinant. And then minus 2, and the determinant of leftover is going to be this, 2, 0, and 2, 1. And plus 3, and the determinant of leftover is 2, 1, 0, 3. Now I'm just going to calculate them. So 2 by 2 determinants are calculated by the rule which we introduced in the beginning of the class. So I have over here 1, and here 1 minus 6. 1 minus 6. Minus 2, and here I have 2 by 1, which is 2, minus 0. So it's going to be 2, and plus 3, and here 2 by 3, which is 6, minus 0, which is nothing, right? So now I'm just going to combine all the numbers and get the final answer. So here 1 minus 6 is minus 5. Minus 2 minus by 2, it's minus 4. And plus 18, so I'm going to get 9. My final answer is 9. What I'm going to do now, guys, I'm going to use row operations and try to bring it to diagonal form. It's not going to be too hard because there are just two numbers just distracting me from this. And show you that the answer is going to be very, very same. Okay? So I'm going to keep this solution and answer on the board. I'm going to erase something from the top. So it's not necessary to do both ways if you are calculating determinant of 3 by 3 matrix. You can do just like whichever way you like. So example way 1. So I'm going to consider matrix 1, 2, 3, 2, 1, 2, 0, 3, 1. So I'm going to do row operations, and I'm going to start with row number 2 equals row number 2 minus 2 row number 1. So 1, 2, 3. I'm going to get 0 here, multiplying by 2, subtracting by, multiplying by 2 it's 4. 1 minus 4 is negative 3. And multiplying by 2 is going to give me 6. 2 minus 6 is negative 4. Well, we do have 0 over here already, so I don't need to do anything. Now, what I'm going to do? I think I'm just going to add row number 2 and row number 3. So my row number 3 is going to be row number 3 old one plus row number 2, which is going to give me 1, 2, 3, 0, minus 3, minus 4. And I'm going to add this, so 0, this minus 3 and 3 is 0, minus 4 and 1 is minus 3. So now I got this upper triangular matrix. All numbers are above the diagonal. Diagonal is over here. I'm just going to multiply diagonal elements. Minus 3, and I'm going to get 9. The very same answer. Well, I don't know. Depending on like what is more clear for you, you can use either way. Okay. I'm going to give you a matrix and will ask you to calculate it on your own. And then I'm going to show you solution. I'm going to do solution two ways, but again, it's not necessary to do it two ways. You can do either one, way number 1 or way number 2. And a good news, guys, we are not going to cover Cramer's rule, which comes in section 2, because I think I'll really believe that you're going to forget Cramer's rule by the time you need it. So determinants you are going to remember a little bit, but for Cramer's rule, but if you wish, you can go over Cramer's rule. It's not a very difficult one. So the matrix is 3, 1, 2, 0, 0, 1, and 1, 2, 3. Okay, so I'm going to count to 5 and start solving it. 1, 2, 3, 4, 5. Well, I don't know. I'm going to start with way number 1. Way number 1. Well, what is going to be good over here, guys? I'm going to switch row number 2, number 3, and write it down like 3, 1, 2, 1, 2, 3, 0, 0, 1. Well, my goal is to make it a diagonal matrix, right? Now it's closer to diagonal matrix than this way. What happens when I switch rows? I'm going to have a minus. One of the first rules about determinants is that when you switch rows, you're going to put minus in front. Okay, now what I'll need to do, I'll need to eliminate this 1, right? How can I do this? Well, row number 2 equals old row number 2 minus 1 over 3 row number 1, right? And that's going to give me 3, 1, 2 minus in front. And if I multiply 3 by negative 1 over 3, I'm going to get negative 1, which is going to give me 0. This one is negative 1 over 3. A number is not going to be very nice. It's going to be what? 5 over 3, I think. And 2 multiplied by 1 over 3 is going to be minus 2 over 3, 3 minus 2 over 3. Okay, I'm going to just write down 2 and 1 over 3 here. That's not going to be important, actually. 0, 0, 1. And product of diagonal elements is going to be 3 by 5 over 3 by 1, which is going to give us 5. And I'm forgetting about this minus, so I'm going to put a minus here, and I don't think a minus is going to fit here, minus 5. Okay, way number 2, using expansion, is going to be 3, 1, 2, 0, 0, 1, 1, 2, 3. So I'm going to write down 3 and determinant of complementary matrix, minus 1 and determinant of whatever is left over, 0, 1, 1, 3, this 2 and this 2 elements, and plus 2, and that's a 0, 0, 1, 2. Well, what I'm going to have over here, it's 0 by 3, which is 0 minus 2, so it's 3 by negative 2. Here I'm going to have 0 by 3 and minus 1, so it's minus 1 by negative 1. And here the determinant is going to be equal 0 because the whole line is equal 0, whole row is equal 0. I'm going to plus 0. So now I'm going to just add up everything and see what I'm going to have. This is minus 6, right? And this is going to be plus 1, so I'm going to get the very same negative 5. You don't need to do both ways. You can choose the way you like more and do it that way, the way it's easier to remember for you. Okay, we're not going to cover Cramer's rule in this section 2, so that's all from section 2, what we are going to learn. Thank you.